Hey everyone, and welcome to this explainer. I am absolutely thrilled you're joining me today because we are going to master the fundamental art of programming. We're talking about mapping out software solutions before you write a single line of code. Think about it for a second. You wouldn't build a house without a blueprint, right? So why in the world would you try to build a complex software program without one? By the end of this explainer, we're going to unlock the true power of algorithms and flowcharts so you can tackle any problem with crystal clarity. Okay, let's dive into our roadmap for today. First up, the power of pre-planning. Then algorithm anatomy, followed by the visual blueprint. After that, we'll hit syntax and operators, core control structures, and we'll wrap it all up with some applied examples and a solid recap. All right, moving right into section 1, the power of pre-planning, why we plan first. So here's the fundamental why behind everything we're doing today. The university manual puts it perfectly. The program written without proper pre-planning has higher chances of errors. It is so incredibly tempting to just open up your code editor and start typing. We've all been there, but honestly, skipping the planning phase is just a one-way ticket to chaos. Algorithms and flowcharts are these amazing tools that clarify every single step before you even touch a programming language.
Which brings us to section 2, algorithm anatomy, breaking it down.
So what exactly is an algorithm? Simply put, it's a sequence of unambiguous steps to solve a particular problem. The word itself actually comes from the mathematician Al-Khwarizmi. And what's really brilliant about an algorithm is that it doesn't care what programming language you're using. It is completely language independent. It's just an ordered set of instructions, which makes it absolutely perfect for debugging your logic way before you get tangled up in code syntax. Now, every algorithm has to follow a strict set of characteristics. It might take an input, but it absolutely must produce at least one output. The instructions also need definiteness, meaning they have to be 100% clear, no ambiguity. But I want to heavily emphasize this last point, finiteness. Your algorithm must actually terminate after a finite number of steps. A super common trap for beginners is accidentally creating an infinite loop where the program just runs forever. Finiteness guarantees we always have an endpoint. Writing an algorithm is honestly a lot like following a recipe. It breaks down into 4 basic steps. First, define your inputs. If you're calculating the area of a rectangle, you need a height and a width. Second, define your variables. And here's a massive pro tip. Use meaningful names. Don't just use h and w, actually name them height and width. It makes your logic so much easier to read later on. Third, outline the operations, like multiplying height and width to get your area. And finally, output that result.
All right, now that we've got the text steps down, let's jump to section 3, the visual blueprint, understanding flowcharts.
A flowchart is quite literally a diagrammatic representation of your algorithm steps. Fun fact, the first design dates all the way back to 1945, created by John von Neumann. You can think of it as the architectural blueprint of your software. During development, it communicates your logic incredibly efficiently. But maybe even more importantly, after a program is built, a flowchart makes continuous system maintenance a total breeze because anyone can just visually trace the operations. To draw these blueprints, we use standard universally recognized symbols. We use an oval to start and end the flow. A parallelogram is strictly for input and output operations like reading a number. Your rectangle is the processing box, used for all your arithmetic and data manipulation. Then you have the diamond, which is for decision-making, branching out based on true or false conditions. We connect all of this with arrows to show the flow line and use a circle as a connector if we run out of space on the page. Just a quick heads up, a classic exam mistake is using the wrong shape, like shoving a math equation inside a diamond. Keep your shapes tied exactly to their functions.
Let's shift gears a bit for section 4, syntax and operators, the math and logic. Let's take a look at the core mathematical operators we use inside those processing blocks. For assignment, we use an equal sign or a left-pointing arrow to store a value, like height equals 5. Then you've got your standard math operators, plus, minus, asterisk for multiplication, forward slash for division, and the caret symbol for power, so a caret 3 is a cubed. But pay really close attention to the percentage sign. In programming, this is the remainder or modulo operator. A modulo b gives you the remainder of a divided by b, which is insanely useful. Also, remember that a statement like r equals r plus 1 is not basic algebra. It actually means take the current value of r, add 1, and store that new value back into r. So the absolutely crucial point here is understanding the difference between assignment and equality. A single equal sign assigns a value, but a double equal sign checks if two values are equal. For not equal, we use an exclamation mark and an equal sign, or sometimes a hash symbol. We also use relational operators like less than or greater than. Finally, our logical operators string conditions together. And means the result is true only if both conditions are true. Or means it's true if at least one is true, and not simply flips it, reversing a true or false outcome.
Armed with our operators, we arrive at Section 5 control structures, directing the flow.
The first control structure is just sequence, reading top to bottom. But things get a lot more interesting with branching and looping. Branching, or selection, uses if-then or if-then-else statements. It checks a condition, and if it's true, it explores one path. If false, it takes an alternative. It basically just splits the path once. Looping, on the other hand, allows a statement to execute repeatedly. Using a while loop, it runs as long as a condition is true. A do-until loop runs until a condition becomes true. There's also the unconditional go-to statement, which just forces the flow to immediately jump to a specific step.
Okay, time for the action phase. Section 6, Applied Examples and Recap.
And this brilliantly illustrates everything we've just learned in one neat package. Check out this flow. We start with our oval. Then, we use a parallelogram to input the value of A and another one to input B. Next, the flow drops into a rectangle for processing, where we assign sum equals A plus B. Then we bounce back to a parallelogram to output or print that sum. Finally, an oval to stop the whole thing. It's sequential, it's highly visual, and every shape perfectly matches its function. When you're building algorithms for math problems, you really need to know these essential formulas. For temperature conversions, notice how the manual explicitly uses floats, like 5.0 divided by 9.0, rather than just 5 divided by 9. This ensures real mathematical accuracy. We also have the area of a triangle using the square root of s times s minus a, b, and c. And for finance, simple interest is just principal times rate divided by 100.0, while compound interest uses that power operator n we talked about earlier to compound the rate before subtracting the principal. Now let's look at a few classic logic patterns for variables. If you ever need to swap the values of two variables, the standard way is using a third temp variable as a holding container. But the manual shows a really clever math trick to swap them without a temp variable. You just add them together, a equals a plus b, then subtract to isolate them, b equals a minus b, and a equals a minus b. Pretty cool, right? Also, for finding the maximum of three numbers, the most efficient method is to assign a variable called big to the first number, a. Then you sequentially check if b is greater than big, and if c is greater than big, simply updating the variable as you go. Dealing with series and sequences requires loops and some clever operator usage. Remember that modulo operator? To find even or odd numbers, just check if I modulo 2 equals 0 for evens or 1 for odds. Easy! When summing a series from 1 to n, you initialize sum to 0 and loop through, doing sum equals sum plus I each time. If the series alternates signs, like positive then negative, you can use the trick term equals negative term times x inside your loop. And for a multiplication table, just loop I from 1 to 10, multiplying it by your target number. Moving on to advanced math, like the Fibonacci sequence. You initialize a to 0 and b to 1, then loop by creating a next variable that adds a and b, essentially shifting the variables down the line. When calculating roots for a quadratic equation, you calculate the discriminant first, b squared minus 4 times a times c. And here is a critical edge case to memorize for your exams. Before you ever attempt to find the square root, you absolutely must check if that discriminant is less than 0. If it is, your algorithm has to stop and print that the roots are imaginary. Our final set of logic patterns involves primes, factors, and common denominators. To check if a number is prime, you actually don't need to check every single number up to it. The manual highlights a massive efficiency trick. Calculate the square root of the number and only loop your checks up to that square root. If the modulo of the number and I equals 0 at any point, boom, it's not prime. For the greatest common divisor, we use a loop dividing the numerator by the denominator until the remainder is 0. And for factorials and divisors, while loops are your absolute best friend.
And that brings us to our final section, recap and thoughts, blueprint mastery.
Programming is never just about typing syntax. It's about structured thinking. You have to analyze your problem step by step, assign clear, meaningful variables. Choose whether your logic requires a sequence, branching, or looping. The algorithms and flowcharts we've explored today are quite literally the architectural blueprints of the entire software world. So my final question to you is this. Now that you have the tools, will you take the time to master the blueprint before you try to build the code? Thank you so much for joining me on this explainer, and happy planning!